Hello all, this is Nadisha and I'm going to present to you Flyweight. This design pattern intends to use sharing to support large number of fine-grained objects efficiently and without incurring high cost. Oftentimes, when developing application, we require multiple instantiation of a single object. This requires a lot of storage in memory and it could be expensive. For example, in a simple text editor application, one would require multiple character objects, row objects, and column objects. This is shown in figure 1 and figure 2 over here. This could lead to a lot of memory usage, and the answer to which is using flyweight design pattern. A flyweight is a shared object that can be used in multiple contexts simultaneously. It acts as an independent object in each context. It's indistinguishable from an instance of the object that's not shared. Flyweights cannot make assumptions about the context in which they operate. The key concept here is the distinction between intrinsic and extrinsic state. Intrinsic state is stored in the flyweight. It consists of information that's independent of flyweight's context, thereby making it shareable. Whereas extrinsic state depends on and varies with flyweight's context and therefore can't be shared. The client object are responsible for passing extrinsic state to the flyweight when it's needed. So, for example, over here, when the row and the character objects are instantiated multiple number of times, the letter A, the letter P, or etc. would be the intrinsic state because that can be shared amongst all the instantiation of that particular object, of that particular character object. Whereas the location or the placement or the coordinate of that particular instantiation is unique to itself and cannot be shared with other instantiations, making the location or coordinates an extrinsic state for that object. Over here in figure 4, the class structure for these objects is shown. Glyph is the abstract class for graphical objects, some of which may be flyweights. The operations that may depend on extrinsic state have to be passed through the parameters. So for example, draw and intersect must know which context the glyph is in before they can do their job. Flyweight patterns, the effectiveness of flyweight pattern depends heavily on how and where they are used. The pattern can be used where all of the following is true, that an application has a large number of objects and because of which the storage cost will be high. The object state can be made extrinsic, so the state of the object can be divided into intrinsic and extrinsic. That's important. Many group of objects may be replaced by relatively few shared objects once extrinsic state is removed. The application doesn't depend on the object identity. Since the flyweight objects may be shared, identity tests will turn true for conceptually distinct objects. The class structure, the diagrammatical structure for the flyweight pattern is shown on the right. The participants in the structure are flyweight, which declares an interface through which flyweights can receive and act on extrinsic state. The concrete flyweight that implements the flyweight interface and adds storage for intrinsic state, if any. The concrete flyweight object must be shareable. Any state it shows must be intrinsic, and that is, it should be independent of concrete flyweight objects context. Unshared concrete flyweight, not all flyweight subclasses need to be shared. The interface enables sharing. It doesn't enforce it. It's common for unshared concrete flyweight objects to have concrete flyweight objects as children at some level in the flyweight object structure. The flyweight factory creates and manages the flyweight objects, ensures that the flyweights are shared properly When a client requests a flyweight, the flyweight factory object supplies an existing instance or creates one if, if none exists. The client maintains a reference to flyweight or flyweights, computes or stores the extrinsic state of flyweights. So in collaboration, how do these classes collaborate with each other is that the intrinsic state is stored in the concrete flyweight object, and the extrinsic state is stored in the is stored or computed by the client object. The client can never instantiate or should not instantiate a concrete flyweight object directly. It should always be via the factory. As it's true, there are consequences for everything. The consequences for the flyweight design pattern is that it has high runtime costs associated with transferring, finding, or computing extrinsic states, especially if it was formerly stored as intrinsic state. However, such costs are offset by space saving, which increase as more flyweights are shared. The storage savings are a function of several factors, naming the reduction in the total number of instances that come from sharing, the amount of intrinsic state per object, whether an extrinsic state is computed or stored. When implementing a flyweight pattern, considering the following issues would be the key point. Number one would be removing extrinsic state. So the pattern's applicability is determined largely by how easy it is to identify extrinsic state and remove it from shared objects. Removing extrinsic state won't help reduce storage costs if there are as many different kinds of extrinsic state as there are objects before sharing. Ideally, extrinsic state can be computed from a separate object structure, one with far smaller storage requirement. The second point to consider is managing shared objects. Because objects are shared, clients shouldn't instantiate them directly. The flyweight factory lets clients locate a particular flyweight, and flyweight objects often use an associative store to let clients look up flyweights of interest, like a key value pair in a hash map. So now let me walk you through the sample code that I try to understand the flyweight pattern. I try to instantiate rectangular class, the object rectangular class, in multiple forms of colors. For this, the size was one of the data fields that was used across all the instances of this object, and therefore I inferred it to be the intrinsic state of this object, and the extrinsic state was the color field because it was unique to each instantiation. This instance of rectangular object was tracked in a hash map in the shape factory method, shape factory class, where the key was the color and the value was the instance of the object of the rectangle. The flyweight pattern class invoked the shape factory method, which in turn used the class rectangle, which implemented the shape factory. So here's my implementation in Java for flyweight pattern. The shape interface looks like this, which is implemented in the rectangle class. The rectangle class has two data types. One is extrinsic in state and the other is intrinsic in state. The shape factory has a hash map of rectangle having key as color and value as the rectangle object. Whenever a request comes to create a rectangle of particular color to shape factory, it checks the rectangle object in its hash map. If the object has the rectangle that's needed, the object is returned. Otherwise, a new object is created and stored in a hash map for the future use, and that's returned to the client. The flyweight pattern, the main class, the client class over here, uses the shape factory to get the shape object, which will pass the information to the shape factory, that is the color, to the shape factory to get the desired rectangle of the desired color. If I run this right now, without writing much of like many lines of code, over here I have multiple instances of the rectangle class with different colors. So these probably are being used over and over again as they are called. The known uses for flyweight pattern is the ET++ library. This is a library implemented in C++. It facilitates the development of highly interactive application that has user interface and data structures and other resources. The ET++ uses Flyweight to support look and feel independence. The look and feel standard affects the layout of user interface elements and their decorations. A widget delegates all its layout and drawing behavior to a separate layout object. Changing the layout object changes the look and the feel even at runtime. For each widget class, there is a corresponding layout class. An obvious problem with this approach is that using separate layout objects doubles the number of user interface objects. For each user interface object, there is an additional layout object. To avoid this overhead, layout objects are implemented as flyweights. They make good flyweights because they mostly deal with defining behavior, and it's easy to pass them what little extrinsic state they need to lay out or draw an object. The layout objects are created and managed by a look object. The look class is an abstract factory and retrieves a specific layout object with operations like get button layout, get menu bar layout, and so forth. For each look and feel standard, there is a corresponding look class, look subclass that supplies the appropriate layout objects. The related design patterns are the related design pattern is the composite design pattern, which is often used in combination with flyweight to implement a logically hierarchical structure in terms of a directed acyclic graph with shared leaf nodes. So this was me, Nadisha, presenting flyweight pattern. The material for this presentation has been taken from the book, the course book, that's the Design Pattern Elements of Reusable Object-Oriented Software.